Welcome to Lona's final Matter, Energy, Space, and Time project. Today, I'm going to be talking about time.
You see here is a student working in the reg study room at around 11:30 p.m. I can draw a digital clock here. The assignment is due at 11:59 tonight, and the student has been working extremely hard on the assignment. Now you're the student's friend, and you're standing outside the reg waiting for them to finish and come out, as they said they would. So you assume that they've submitted the assignment by now. It's 11:53, and you're just waiting for them to come out. And we should be able to assume that the student will submit all her assignments on time. Quantum mechanics says otherwise. You see, according to the Copenhagen interpretation of quantum mechanics, we can only calculate the probability of the student completing the assignment. So nothing is conclusive without measurement according to this interpretation of quantum mechanics. But according to the many worlds interpretation, the student has and has not completed the assignment, submitted it. This introduces the concept of multiple realities, one in which all outcomes are real but depend on who is observing it. And if the student has submitted the assignment, that is true for that reality, whereas for the Copenhagen interpretation, one would have to observe and confirm the fact that the student has submitted the assignment before confirming that the submission is real.
Now that we've gone through a solid example, let's see how time is actually even much stranger than that.
Did you know that time moves differently for someone who's on top of a mountain, whereas someone who's on the ground? Their clocks aren't going to align the same. So these two people are going to experience time differently. If they both have clocks, they're going to say slightly different things because of the way time moves differently in different altitudes and different places. Time would also move differently for people on two different planets, for example. And if these are both foreign planets and they come back home to Earth, they might be completely different ages. So the way that time varies in these different situations can be described by the term time dilation.
We can actually quantify the way we see time. And here's a solid example of how we can see the way that time differs, whether something is moving or whether it's stationary.
Let's say we have a light hitting two mirrors. So the light comes on from mirror A and it hits mirror B, and then it bounces back to mirror A. So mirror B is going to be this one, and then this is going to be mirror A. The mirrors aren't moving, they're staying the same. Light is the same, so we can describe this situation as situation S prime. What if the mirrors were moving? In that case, so let's just say that B and A were moving like this, or I can't make them move in a straight line, but imagine they're moving in a straight line, each of them at the same speed and at the same time. If both of them are moving, then that means the point that the light hits B will already be over here. So the light's actually going to look more like this by the time it hits A again, meaning that the combined distance becomes much greater. As you can see, it looks like a triangle, whereas the other one looked much shorter. Thus, from an observer's point of view, the clock, if this represents time, the clock ticks faster for S prime than for S, since the distance between the lights are much shorter. We can use a specific equation, change in t prime equals change in t over the square root of 1 times v of s divided by c squared, to quantify this difference. If we assume that the velocity in the situation of s is 80% of the speed of light, so 0.8 c, and we plug that into the equation, we can see that change in t prime equals 1.67 times change of t. So that means that when 1 second passes for s, 1.67 seconds have already passed for s prime.
Let's talk to some scholars to see what they think about time.
Are we at rest when we're on Earth? Well, according to a scholar named Lingerford, even if you stand absolutely still in your math class, you will not be at rest from the perspective of an observer out in space. Why? Because the Earth is falling around the sun at the velocity of 100,000 kilometers per hour. And according to Lingerford, the sun is falling in the Milky Way too. And the Milky Way falls as well, making nothing you can truly conceptualize at rest. Even measurements of time by ultra-specific methods like the TSC and DISC methods, which is traditional self-comparison and drift-insensitive self-comparison methods, show differences in time. As you can see, there's tons of differences here. of the optical lattice clock, which helps with verifying general relativity and other space-time phenomena. So even the optical lattice clock has differences in time. Thus, time is weird.
Initially, this might not seem as mind-blowing as it actually is, because you yourself have participated in time dilation by the way you think about time. You've probably heard of the phrase, time flies when you're having fun. And you've probably experienced the way things seem to take much longer when you're staring at the clock versus when you're actually doing things in your routine over and over again. During an experiment, it was shown that the subjective duration of unexpected or infrequent stimuli is overestimated as compared to expected and frequent stimuli, meaning that you often perceive surprise events as much longer than they actually are, and regular routine events as shorter. So time changes and is subjective and strange even by the way you perceive it.
Carlos Rovelli puts it in simple term in his book, The Order of Time. He writes, "For everything that moves, time passes more slowly." Rovelli specifies that we can represent time that is stationary by t and time that is moving by t prime. So if a clock is stationary, then it's going to be t, but if a clock is moving all around, then it is going to be represented by t prime. Someone who's wearing their Apple Watch, that clock is going to move at t prime, versus someone who's going to just stand there with the clock is just going to be t. Furthering the complexity of the concept of time, he writes, "There's not a single time for any particular place. A duration can be associated only with the movement of something, with a given trajectory. Proper time, then, depends not only on where you are, but also on the speed at which you move." Now we can get back to our original situation of the student turning in her assignment. We've talked about the weirdness of quantum mechanics in that situation, but we can also talk about the weirdness of time. If we can say 11:59 is an arbitrary number, and whether or not the student submitted before 11:59 is arbitrary, since time itself is a concept that is very strange and evolving and can think about it in different ways. So thank you so much for listening, and I hope you have a wonderful day.